to. All right, so tonight we're talking about resistors in series and in parallel. And I will try to not make it confusing because it really isn't, it really shouldn't be. When you have resistors in series, I have a source of voltage, current comes out of that voltage source, goes into the first resistor, then the second, then the third, and the total resistance in the circuit, if all we have is resistors one after the other, we call that in series, all in a line somehow. That means that the total resistance, all we're doing is adding them up. Resistor 1 plus resistor 2 plus resistor 3. That's resistors in series. So here we have an example of resistors in series, and what you do when you're analyzing a circuit is you simplify it. So we have a 12-volt battery, and current coming out of that battery flows into a 6-ohm resistor, then a 3-ohm resistor. So since those two resistors in series, all we do is add them up, 6 plus 3 is 9, we can simplify the circuit and say, okay, that's the same as though I had 12-volt battery with one 9-ohm resistor. So we have a 6-ohm resistor, 3-ohm resistor connected in series to a 12-volt battery. Assuming the battery contributes no resistance to the circuit, and we will make that assumption, find the current, find the power dissipated in each resistor, and the total power delivered to the resistors by the battery. All right, so the power thing is something we mentioned briefly, and we will go through how we do that now. But the current, so all the current flows out of the battery and comes back into the battery. So all of the current has to go through each resistor. So if the total resistance is 9 ohms and the voltage is 12 ohms, V equals IR. Therefore, I equals V over R, 12 volts divided by 9 ohms of total resistance. 12 divided by 9 is 1.33 amps. This equivalent resistance circuit gives us the ability to figure out how much current comes out of that battery. Now I know that the 6-ohm resistor will have 1.33 amps flowing through it, and the 3-ohm resistor will also have 1.33 amps flowing through it. Power equals current times voltage, or we can say, since V equals IR, we can say power equals current times resistance. So power equals I squared R. So the power for the 6-ohm resistor is going to be 1.33 amps squared times 6 ohms of resistance. Power consumed by the 6-ohm resistor is 1.33 squared times 6, 10.6. And it's funny because I'm teaching physics 1 by day and physics 2 by night. And in physics 1 right now, we're in chapter 7 or 8 where we talk about power. Power is energy transformed over time. It's a brief topic in physics 1, and then we revisit it in physics 2. It's watts. Joules per second is power, watts. In the old days, we would have a 60-watt light bulb or a 100-watt light bulb, and we'd have an idea of how bright those were. That's watts of power, joules per second, and we just do a capital W for watts. Power for the other resistor, power for the 3 ohm resistor, same process, I squared R, 1.33 amps. It sees the same current, but it's a different resistor, 3.33, 1.33 times 3 ohms, 1.33 squared times 3 is 5.3 watts. And then the total power delivered to the resistors, you just add them together. So I guess that's 15.9 watts total. Maybe the answer's on the next page. I don't remember. It is. So, so the first step of any of these problems where you have multiple resistors will be to simplify the circuit, the equivalent resistance of the circuit. By simplifying, if it's all resistors in series, really easy, just add them all together. Resistors in parallel will be a little more complex, and then complex circuits where you have resistors in both series and parallel will be a lot more complex. Hold on one brief moment while I shut off my oven. Dinner will be yummy, but I don't want it to burn. Okay. We don't need to worry about this. They're trying to just give some real life examples. Okay, here's when you have resistors in parallel, so you have a source of voltage and you have one resistor in that circuit, but then you decide to do another resistor, but just connect it entirely separately. So there's another resistor connected to that voltage source that doesn't care that the other one is there at all, is unaware that there is another resistor. It's just a whole other pathway around. So usually when we see 2 resistors in parallel in a circuit, and it's only the pathway that matters. They don't literally have to be drawn in the middle of 2 parallel lines for them to be parallel, arranged in parallel in a circuit. But, you know, in this first exposure, trying to keep things as obvious and simple as they can be. So we have 2 resistors, they're in parallel, and there's a complete pathway. And if I pulled one of these resistors out, the other one would be totally unaffected. But the math is a lot more difficult. This is, you know, this literally isn't my life, but I will frequently, I have electric circuits in my kitchen, and this is where I will always make the mistake of turning on the coffee maker and the space heater and then the microwave at the same time. And the more things you have in parallel, the more current gets drawn from that circuit, and the more likely you are to trip a circuit breaker in your house that is only rated for, say, 20 amps. So if you try to draw more than 20 amps all at once, you're going to heat things up, potentially cause a fire. And so the circuit breaker shuts off and says, whoa, that's too much, all on one circuit. You should plug in somewhere else. And so I wrap the cord around the corner and get onto another circuit for my space heater. oh, some examples, you know, analogies, but here's the punchline. If you're only going to listen for 5 minutes in tonight's lecture, make it be the next 5 minutes. When you have resistors in parallel, it's like you have a big barrel of water. So it's a tall barrel and there's water in it. And then each resistor is poking a hole in the bottom of the barrel, you know, just a small hole. But when you poke a hole, some water starts flowing out. If you poke another hole, even more water starts flowing out. Another hole, even more. The more holes you have, the lower the total resistance is going to be. The more resistors you add in parallel, the lower the total resistance is. So if I had 3 resistors here and they were of, well, yeah, 5 ohms, 10 ohms, and 15 ohms, the total resistance is not 20, 30. It's not 30. It's going to be really small. The more resistors in parallel, the lower the total resistance. So 1 over Rp equals 1 over 5 plus 1 over 10 plus 1 over 15. 1 over 5, 1 over, is 0.2, plus 10, 1 over 10 is 0.1, so 0.2 plus 0.1 is 0.3, plus 1 over 15, that's 0.06. So the total, when I add 1 over 5 plus 1 over 10 plus 1 over 15, I get 0.366. That is not the answer. I am not done yet. I figured out what 1 over Rp is, 1 over what the parallel resistance is. So now I have to invert this. I have to do 1 divided by 0.366, and I get 2.72 ohms. So there's 3 resistors. We'll draw in another pathway, R3. There's 3 resistors in parallel, 5, 10, and 15 ohms. But when I put them all in parallel, the total resistance for the 3 of them is lower. It's only 2.72 ohms total. That is confusing. We will do more examples, but that's a thing. Okay, so here we have a 6-volt power source. They do the squiggly line, so this is alternating current. Doesn't matter for our purposes. We have an 8 ohm resistor and a 4 ohm resistor arranged in parallel. And so we want to do the parallel equivalent resistance. They gave us the answer, but let's just make sure we get the same answer when we do it, so we know what we're doing. 1 over Rp equals 1 over 4 plus 1 over 8. 1 over 4 plus 1 over 8, 4. 1 over is 0.25 plus 8, 1 over 0.125. The 0.375 is the answer there, but I'm not done. Rp equals 1 divided by 0.375, 2.67. Clear all drawings, close that, stop share for a quick second, just to say, oh, I can do this, I know I can. There is a button on my calculator that is 1 over. Do you see it? I don't see it right now, but I know it's there. Beneath the sign button, 1 divided by X is the button right beneath my sign button on my calculator. Having that button makes these problems so much easier for me. So my TI-30 calculator, which is fairly cheap at a Target or Walmart, is worth it for this kind of problem. If you don't have this kind of a calculator and you're working it out some other way, just remember that final step, 1 divided by what you get when you do 1 divided by this plus 1 divided by that. Okay, voltage 6 volts, determine the equivalent resistance of the 2 speakers, total current supplied by the receiver. So again, we're all about Ohm's law. Oh, I'm not showing you the problem, but I'm looking at it. Here we go. So the total current that's coming out of our power supply is going to be current's coming out of here and going into the equivalent resistance of 2.67 ohms. So V equals IR, I equals V over R. This R is always the equivalent resistance. The V is always the total voltage. So 6 volts divided by 2.67 ohms. 6 divided by 2.67 is 2.25 amps. And then power dissipated by each. Again, we can do the same deal we did before. So power equals I squared R. And we can take the current squared times the resistor and figure out how many watts for each of our speakers. We don't need to do that all over again, but you'll know the process. So here's the piece of figuring out the parallel resistance, the current, and then the 2 powers. They did IV instead of I squared R, which is another way to do it. You get the same answer. So there you go. And yeah, maybe I didn't mention that each of the resistors will draw current as though it's there all by itself. So when we figure out the current through the 8 ohm resistor, it's just 6 volts divided by 8 ohms, 0.75 amps. And then the other one is 6 volts divided by 4 ohms, 1.5 amps. The total current is these 2 numbers added together. So 1.5 plus 0.75 will be the total 2.25 amps. So the total current coming out of the voltage source will divide up over the 2 pathways in parallel resistors. Okay, we don't need to do a 3-way light bulb, but we do need to tackle complex circuits, and circuits will get more complex than this, but this is a good start for complex circuits, and maybe as complex as we're gonna get, but in real life, they get worse. All right, so current comes out of the battery and it sees this 110 ohm resistor. this 110 ohm resistor must be in series with whatever's after it, because it has to go through there to anything else. Then we get to this point labeled A. We'll call this a junction. This junction A provides two different pathways that ultimately lead back to the other end of the battery. If there are two different pathways that go back to the battery, then those two pathways are in parallel with each other. If we go through the 180 ohm resistor, well, then we're back at the battery. So that's the end of that trail. But if we go to this 220 ohm resistor, this one, I have to go through that and then through a 250 ohm resistor before I'm going back to the other side of the battery. So these two are in series with each other. So I have one in series with two parallel pathways. One of the parallel pathways has two resistors in series. So that's why it's kind of highlighted in yellow here. So what I'm going to do is simplify the circuit. What if I take these two resistors out? They're in series with each other. Series resistors is just adding them together. And I'll replace these two with one resistor. Now I have my 110 ohm with two parallel pathway, with one pathway that is parallel, two resistors in parallel, 180 ohm, 470 ohm. Now what I do is the equivalent resistance of two resistors in parallel. Parallel, remember, is 1 over RP equals 1 over 180 ohms plus 1 over 470 ohms. 1 over RP, this is going to be some weird numbers. 180 inverted is 0.0055, it's a very small number, plus 470 1 over 0.002. So 1 over RP is 0.00768. If you get really tiny numbers and you think that that's your resistance, remember that you probably missed this last step where you invert it. 1 divided by 0.00768. And when I do that, I get 130. So these two resistors, two big resistors in parallel, give me an equivalent resistance that is smaller than either of them alone. And it's an equivalent resistance of 130 ohms. Now I've simplified my circuit from 4 resistors down to 2 resistors. Those 2 resistors are in series with each other. So I just add them up again. 110 plus 130 is one equivalent 240 ohm resistor. Now I would go through this process if I wanted to figure out how much current. I'd have to go through this process to figure out how much current is coming out of my battery. So the current out of my battery, IBAT, equals V over REQ. So the voltage is 24 volts. The equivalent resistance of the whole circuit is 240 ohms. So that would be 0.1 amps is the total current coming out of this battery. And then I could ask any question. I could ask you, how much power is consumed by the 110 ohm resistor? And you'd say, well, power equals I squared R. So I know that there's 0.1 amps going through the 110 ohm resistor. So 0.1 squared times 110 ohms. And I would know how much power is consumed by that resistor versus any of the other resistors. There'd be different values because the current is going to split up after the 110 ohm and some will go this way and some will go that way. And so I would have to figure out how much current goes through each part of this circuit. All right, clear all drawings. Batteries do offer some small amount of resistance, but we will not bother doing anything with that because that will just confuse things. Okay, there is another aspect to dealing with electric circuits besides just Ohm's law. And this stuff with Kirchhoff's rules, and that's how I've heard it pronounced. Don't get thrown off in anything in science by pronunciations. I will never make fun of you for pronouncing something wrong. I might try to figure out what you're talking about if I don't understand it, but there's all sorts of weird things. But I've always heard this pronounced Kirchhoff's rules. And goodness, you know, back when I was in college, we were just guessing at how to pronounce things. And nowadays, anybody can look up anything on a YouTube video and maybe come to some kind of consensus with how people pronounce words. But Kirchhoff's rules is basically saying that, you know what, I could look at any point on a circuit and current can't just sit there on any space in a wire. Any current that goes into a junction has to leave. So if 7 amps goes into this junction, then 7 amps has to leave that junction. It can't just sit there. So Kirchhoff's junction rule says that the total current directed into a junction must equal the total current directed out of that junction. And the loop rule says, you know what? If I start at the top of the 12-volt mountain and I drop 10 volts over one resistor and another 2 volts over the other resistor, I must be down at 0. So 12 minus 10 minus 2 equals 0. Those are Kirchhoff's rules. And so in ridiculously complex circuits, there are ways to figure out what's going on in a circuit using the junction rule and the loop rule. And I'm not going to have you do the math for that because it involves a lot of solving simultaneous equations, which is maybe a good exercise to do sometimes, but it takes up pages and pages and it doesn't really do anything for your total understanding of physics. So what I might do is have you write out the equations for Kirchhoff's rules, but not have to solve them. And that would look something like this: IR plus the voltage plus IR equals the total voltage, and you would have an answer. So when you apply Kirchhoff's rules, you pick a direction to go. Even if you're wrong, all you would do is get a negative sign for current, and that would tell you that actually the current's flowing the other direction, and you would write out equations. And that's enough of this stuff. So here, just remember that capacitors were the opposite of resistors. Resistors in series, you add them up. Capacitors in series, we do this 1 over CS plus 1 over C1 plus 1 over C3, the inverted thing. And then capacitors in parallel were the same as resistors in series, where we just add them up. That is enough of that. Okay, let me stop share. All right. I have a quiz for you on chapter 29. material. So I need to find our Canvas page again so I can oh, I will get there. Share the Canvas page. So I have a quiz for you on chapter 20, and I made it darker blue in bold, chapter 20 quiz. And I am delighted to answer any questions you have from the chapter 20 homework before you take on the quiz. So a lot of nanos and micros in here. Nano is 10 to the negative 9th, micro is 10 to the negative 6th. And I should have updated this to not include the links to the questions because they're from another semester. So they would only mess you up. Sorry about that. Oh, just delete it. Save. Okay, sorry. This has been a rough semester, has it not? I just gotta find the chat. I know that it's there and chat. I see it. 24. Yes, delighted to go over 24 from the homework. All right, so there is up here somewhere a description of how you put together a resistor. And I don't actually see that equation. The deal with resistors, we'll just go to me for a minute. There was an equation in the chapter. Oh, come on, blah, blah, blah. So resistance is this rho L over A. Rho is the value for the particular material that we're using, and then length and area. So yeah, I guess I was doing it right there. So the resistivity rho for copper, 1.72 times 10 to the negative 8th, and then length over area. And so we have the length 20 meters, and then we have 2.053 millimeters in diameter, and then area is pi r squared. So we have to take this diameter in millimeters, convert it to meters, divide it by 2, pi r squared, and then the length 20 meters. I don't think I have a question like this on the quiz because I decided that it was just kind of a mathy problem and not really a physics question, but that's how you do that. If I had that question on the quiz, I would have given you the equation, and I just didn't because I don't have it on the quiz. Sorry if that was a pain in the butt on the homework. Other questions? Power dissipated, power for a toaster. Power is joules per second. And so if it's a 1200 watt toaster, that's 1200 joules per second. And so 1 minute is 60 seconds. So 1200 joules per second times 60 seconds would give you how much energy, and then you can figure out how much that costs. Megavolts 10 to the 6th volts. I don't know why my smart speaker thinks mega sounds like another word that would turn it on. Yeah, I think it's pretty straightforward. Okay, I'm not seeing any other questions. Let me just pop open the quiz and make sure I'm not misleading you on anything. So all the equations you need are here. And we have the lightning flash. You're going to report your answer. Report your answer in gigawatts. Giga is 10 to the 9th. So whatever answer you get at the end, divide by 1 times 10 to the 9th, and that's the number you give me. So here, obviously we want wires to have low resistance. So you want to find something with low resistance. Power. All right, I think you should be all set to take the quiz. Sometimes people have trouble viewing the images on the quiz, so I'll just have the page shared to this image so you can see it. If you have questions while you're taking the quiz, let me know. Otherwise, that's our evening tonight. I'm here on Zoom chat if you have questions, and I will stop recording. I'll post the video.